I welcome all comments. And unusually, if there's something wrong, I really would like you to tell me. Okay, so let's get started. Many of you may have heard of Skolem functions. Some of you may not. It's not scary, okay? So you've got a Boolean formula. It's got quantifiers. There's alternating quantifiers in general. And you would like to not have alternating quantifiers. You'd like to have just one type of quantifier, okay? And so there's a trick where we take, say, the existential quantifiers here in particular, and replace them with functions that specify in this game between the universal and the existential players, what move would the existential player take if the universal player played this prefix of moves, okay? And now this is a formula that doesn't have existential quantifiers in it. There's the functions, but it's only universal quantifiers. These functions I use to replace the existentially bound variables are called Skolem functions. So formally, all right, we've got a first order Boolean formula with everything quantified. Okay, I'm just going to look at the first two quantifiers here. The rest of this may be another quantified Boolean formula. And the Skolem function is just going to be a function that takes the domain for the universal player to the domain for the existential player, such that the truth value or the validity of this formula is the same as if I let the existential player make the move, right? Normally, Skolem functions, we would only think about them for formulas that are true, but here we sort of extend the notion to say, look, if that sentence is not true, the existential player can play anything, okay? And that's useful actually in some applications. I know, right? Applications here. Anyway, for the purposes of today, the domains will just be Boolean strings, and the problem is going to be, given some formula of this form, you want to find a circuit computing a Skolem function. All right. And actually, we're going to mostly focus on, yeah, Ilya?
How are we going to measure what they're just trying to make the connection? Is this related to the Skolem problem?
The Skolem problem. What is the Skolem problem?
Apparently not. Or, I mean, maybe no, you know.
Maybe it is, and I just don't know it.
I was like, it's
I'd like to think Skolem did more than one thing, but I don't really know.
probably. So it's actually in the recursive languages, you have a sequence, and you want to know if the sequence will have a zero element in it or not. Like we have this is the Skolem problem. It's considered to be undecidable, but it's open if it's even decided.
They did more than one thing.
No, I mean, I'm sure.
Yeah.
I was wondering if there's a connection.
I don't think there's an obvious connection.
Okay. But if somebody discovers it, I think that would be a great contribution that come out of this workshop.
Yeah.
Yeah, sorry, as I was saying, for most of this talk, I'm going to focus on the case where phi is propositional, and then this is known as functional synthesis. Okay, you think of phi as being a specification for a function, relating the input and output variables, and so I want to find a circuit that satisfies that specification. Okay. Unlike the other talks in this today so far, I'm actually going to mention MCSP, but only to say that, this is not the problem I'm solving. Okay, but both of them, you're trying to find a circuit. The difference is, of course, for functional synthesis, I was given a specification that just tells me how to check whether or not the function is being computed correctly. Whereas minimum circuit size, of course, you were given a circuit that actually computes the function, which you could use to define a specification like this. Okay. But for functional synthesis, any circuit suffices, whereas of course MCSP, you want a minimum size circuit. Okay. So on the one hand, I'm not actually given a circuit computing the function because then that would be trivial for me, but so I only have the verifier, but I don't have to output something minimum size here. Okay. However, circuit size will play a key role later in the talk. All right. So functional synthesis is still in general a pretty hard problem. Okay. And people are interested in solving it. Okay. And sort of our agenda here is trying to understand sort of special cases of the problem where we can at least do something given some powerful words. Okay. So first of all, as motivation, I'm going to review some relatively recent work by Savovsky, which it gives an approach for solving a unique functional synthesis problem in practice. Okay, so in unique functional synthesis, I'm promised that for every binding A, such that this is a valid formula so that the existential player has a move, that move is unique. Okay, and so like for MCSP, that specification, the output of the circuit was uniquely defined. So Savovsky gives an approach based on interpolation for unique functional synthesis. And again, probably half the audience is very familiar with interpolation and half has no idea. Okay. The proof system has feasible interpolation if there's a polynomial such that when I gave you two formulas where there's common variables x and then distinct sets of variables y and z's, such that there's a refutation of the conjunction of the two of some given size s, then there's a polynomial size interpolant circuit in just the common variables, such that for any assignment to the variables, this interpolant circuit basically tells me which of the two terms in the conjunction is falsified, or at least one of them that's falsified. Okay. And it turns out that from these standard simple proof systems like resolution that we can find in practice with set solvers in many, many cases, from that refutation, you can extract an interpolant function efficiently, very, very easily. Okay, so how does interpolation allow me to solve functional synthesis, or unique functional synthesis, sorry. Well, okay, so for now, let's just focus on a single bit. Okay, and if we said that the specification, sorry, this was a unique functional synthesis problem, then in the cases where there is a witness y, it's not true that both, true and false are witnesses. Okay, so this is an unsatisfiable formula if it was a unique synthesis problem. And in practice, you'd use a set solver to find a resolution refutation. Okay, and now, this interpolant function. Okay, if the interpolant function says 0, the first formula is false, and if it says 1, the second formula is false. Okay, and now if I told you that this existentially quantified guy is true, then when my function says 0 and setting a 1 is false, that means that because the other setting was true, the interpolant function gives me a correct binding. And ditto, when my interpolant function says 1, that's also satisfied. So the interpolant in this case is a Skolem function. Solves the synthesis problem. Okay. And you can extend this to multiple bit functions by finding these Skolem functions one bit at a time. Okay. All right. Well, so here's a method that's solving unique functional synthesis for me. How far could we push this? Okay. How much of a restriction was uniqueness? And so for right now, what I'm going to do is I'm going to assume for the moment that I have an oracle that solves unique functional synthesis for me. And I'm going to show I can get a polynomial time randomized algorithm for general functional synthesis using my unique functional synthesis oracle. Yeah, Ilya?
Maybe a good question, but Can't you use the same trait or unequate the same trait that you can use to move from set to the unique set?
It's a very, 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 very related trick, yes. You have to be a little careful how you do it. But I want to, before we talk about it, I just want to point out that there's a big caveat here, which is that I'm allowing the algorithm to run in polynomial time in both the input and output of the oracle. And I don't have a guarantee that I'm going to get small circuits from the oracle in general. And we're going to return and hammer in on this point later. Okay. So, yeah, I mean, you're going to use hashing. And the question is just, what's the right way to do it? And if you've been around, you've seen that that's how you're going to reduce to unique. Okay, and specifically, I want to use this lemma from Bellari, Goldreich, and Petrank, where you take an n-wise independent hash function, and that's going to guarantee for you that if you have at most this 2 to the I solutions, then after sticking this hash constraint on there, you have at most n squared solutions, where n was the number of bits in the universal player's contribution. And as long as I've got enough solutions, I had at least n squared over 2 with high probability. So this is a little bit more precise. All right, well, n squared isn't quite unique, but there's another easy thing I can do, which is saying, well, okay, give me k, solutions in lexicographic order. Okay, now it becomes unique, right? You can prove that yourself. Okay, so yeah, with these two pieces together, the algorithm kind of designs itself, right? So okay, starting from our formula, just inductively, we have that there's at most 2 to the I solutions. Probably should be m, but forget about that for a minute. And right, so by lemma 1, we have at most this n squared solutions, and so we're going to then iteratively pick out things that have k solutions, k going from 2n squared down to 1, and using our unique functional synthesis oracle to obtain a function that for those inputs that had exactly k solutions for this hash function will give me solutions for those guys, okay? And now I can use my specification to check, all right, did my partial Skolem function on a given input, did that give me a witness yet or not? Okay, so there's this ugly thing, which is just saying, give me the first witness that produced a valid solution for X. Okay. And then, given that circuit so far, I'll say, okay, fine. Now let me just consider the function that did not get a solution in this round. Now I've gotten everybody who had at least 2 to the I minus 1 solutions. So, induction hypothesis holds, and I can continue for the next iteration. Okay, so every time I reduce the number of possible solutions remaining to the formula by a factor of 2, and clearly in a polynomial number of rounds, I finish. Okay, simple, right? Yeah, so that's not a hard theorem, but we don't have a guarantee that the circuits that I get are small in general. Okay, so yeah, moving on. So what happens? Okay, and in particular, where I want to go next is saying, okay, fine. Instead of a unique functional synthesis oracle, let's suppose I just had an oracle for set. Okay? So backing off one stage. Can I just use my SAT oracle to solve general functional synthesis questions? And it's not so clear. The very first thing that breaks is Savosky's method actually is not always finding small circuits for me. Okay, so as an example, consider this version of the bit pigeonhole principle. Basically, Y is supposed to give me an index where there's a collision in the assignment of holes to pigeons in X. Okay. Okay, so, whatever hashing techniques I'm doing on Y here, to try to get a unique, witness out. After I restrict Y in some refutation, I'm going to get a refutation of the bit pigeonhole principle, from my refutation of this pair that we used in Slavoski's method, and we know that that has exponential size. Okay, and so therefore, Slavoski's method gives me an exponential size circuit for this formula. It has to, but there's a polynomial size circuit that just returns the first collision. Okay, so even though there's a small circuit witnessing this formula, the interpolation-based method won't find it for me. Yeah, Mark.
Intuition for that, kind of because like any proof system with feasible interpolation is a kind of a weak proof system. So Silvosky's method, it just intuitively might be limited to finding stuff that you can prove correct in a super weak proof system. I don't know.
So it's not so easy in that, like, again, for feasible interpolation, the computation itself is corresponding to the proofs. I don't know, I guess I'm not an expert in bounded arithmetic, so I don't know what the relationship between the complexity of the proof and the complexity of the algorithm being analyzed necessarily be, except to say that, here, the interpolant function is just, its complexity is not greater than the complexity of the proof. I don't know the other direction. All right. Okay, so we want a different method to try to solve at least the unique synthesis problem. Okay. And there is another method that's gonna work nicely here. And this is inspired by work by this Bashuti, Cleve, Gavalda, Kanan, and Timon on learning circuits with an NP oracle. Okay. Yeah, their idea was to approximate the halving algorithm, which was a mistake-bounded learner. Walko introduced the mistake-bound model this morning, so thankfully this is relatively familiar to you by now. But there it is again. You in rounds, the environment gives you a point, supposed to make a prediction. If the environment tells you what the correct label was, if you were wrong, you make a mistake. You would like to bound the number of mistakes that you make for all possible functions in the class. Okay. The halving algorithm is taking a majority vote of the remaining functions in the class. Okay. And that ensures that whenever you would make a mistake, half of the remaining functions were wrong. So the remaining consistent functions is decreasing geometrically and then in size proportional to the encoding lengths of the representations. You find the correct hypothesis. Okay, good. So yeah, so basically the idea here was they used the ability to generate random samples of satisfying assignments using the NP oracle. And this is using this connection between approximate counting and sampling. Again, using hashing of the right density to capture approximate counting with the NP oracle. Okay, Ilya?
One anecdotal thing about that, the original paper was approximate, but that result that you quoted, this Berlin-Moblike thing, actually makes it better.
So yeah, I mean, you can get very accurate sampling. At this point, though, it's not making a big difference to us. Okay. Yeah, because it's enough for me to say just rule out a constant fraction of circuits, so I can tolerate any. I shouldn't say any, but I can tolerate some amount of slop in, say, the distance from uniformity of my samples. And then also from the fact that I've only sampled like a polynomial number of solutions here, right? So anyway, yeah, so again, I predict according to the majority on my sample. That's a good approximation to, or a reasonable approximation to the proportion of the remaining consistent hypotheses that would predict that bit. Okay, and so, the same analysis basically applies. For circuits of size S, I only make S log S mistakes. Okay, good. Okay, so, Bashudi and friends assumed that we were doing single bit functions. And if I want to extend it to multiple bit functions, I run into a small problem, at least if I do it in a naive way, okay? So I could consider a relation that maybe is easy to verify where the existential player has these two blocks. For a secret setting of the first block, the second block can be answered by a simple function. But for every other setting of the first block, he has to compute a hard function. Okay. And then the problem is that, there are many circuits that could, say, memorize the hard function on a few inputs. And so if I only have to fit, at the start of this algorithm where I'm just trying to either sample random things or only trying to, fit a small number of examples, okay, it's very easy for me to incorrectly guess or not hit this secret setting, get something that computes something outside it, and then I have no hope of computing a small circuit for the second half. Okay, so you have to be a little bit more careful in how you would apply these techniques. But in particular, though, if I just focus on the unique functional synthesis problem, there's not really an issue. Okay, so I can just repeat that algorithm as before. And the key is that because the witness is unique, okay, the small circuit remains consistent with all the examples I've seen so far. So you can solve this unique functional synthesis problem with essentially the Bashudi and friends algorithm. And of course, I didn't need to know the circuit size bound up front. I could check in the end if I get a correct Skolem function. And if not, I can sort of iteratively increase the size bound. So you can do something like minimizing the circuit size in this setting. Okay. All right. So fine, we got the ability to solve unique functional synthesis again with the aid of the NP oracle. And is that sufficient for my reduction? Unfortunately not, because hashing could kick out my small circuits. So yeah. All right. So what's a version of the problem that I can solve? With some something that's slightly more general than a unique solution, but maybe it's not completely general functional synthesis.
Your solution.
Huh?
Your solution.
So that would be great. I'll tell you what I know how to do. And being able to do a few solutions per X, I don't quite know that. What I know how to do is, if there's a subset of indices such that given the settings on those indices, everything else is unique. Okay, I'll call this an anchored relation. And this is, right, so given the anchor bits, the rest of the witness is uniquely determined. So note that you can use this Bashudi and friends technique to just find uniquely determined bits of the witness. Okay, I could just use this for a single bit. Let me provide the other bits of my witness as inputs to the circuit. Okay, and just try to pick out witnesses for single bits given the rest of them. And if I do that, I can replace that with a Skolem function, and then iteratively try to prune off bits that I can predict. So iteratively, I can find circuits for the non-anchor bits. If there's a sufficiently small number of anchor bits, then the remaining indices, I can just, again, try all possible solutions and take the first one that works. Okay. And because I have this specification where I can plug in my Skolem functions for the rest, this is actually efficient. Okay. Right, so I can solve this for these anchored relations. That's sort of the extent of what I know how to do for functional synthesis. Let me now very briefly step back and look at the problem of more general Skolem synthesis. Right, so remember, up till now, we were just focused on, a single alternation where this was a propositional formula. And in Skolem synthesis, there are multiple alternations. And I'm going to consider the case where there's only a small number of variables under the existential quantifiers. Okay, so you can think of it like this. So there's constant number of alternations, and each time the existential player does one bit. Okay, and now I want a tuple of circuits for the player strategy. That again is going to preserve that this sentence is equivalent to this single universally quantified thing where I have the tuple of circuits telling me what the existential player does. Okay. Yeah, so now what I'm going to do is I'm again going to try to follow this Bashudi and friend strategy, except now I'm going to look at tuples of circuits of the desired size, and I'm going to vote according to the plurality of the assignments that I gave to all k bits. Right, so I'm going to give a circuit that on some input, right, says, okay, what's the majority of the votes from the tuples doing on this bit? Or sorry, plurality. Okay. And the point is that, because there's a small number of bits here, every time I find a counterexample, there had to be approximately 1 in 2 to the k fraction of the remaining circuit tuples were consistent with this prediction. Right, there's just, there's not that big a space of like possible tuples of prediction I can make. Okay, and so, yeah, now there's this, 2 to the k overhead in number of iterations because I'm only getting killing a 1 in 2 to the k fraction of the remaining space each time. Nevertheless, if k was constant, this is like O of s log s iterations. All right, to summarize, what were we able to do? We had this reduction from general functional synthesis to unique functional synthesis that did not preserve circuit size. My computer is not about to restart. We saw a randomized point-in-time NP Oracle algorithm for solving unique functional synthesis, or more generally, solving these k-anchored relations. And we saw that I could solve Skolem synthesis with an NP Oracle when I had only a small number of existentially quantified variables. Okay, a couple open questions just to kick off the open question session that we're about to do. One is, do NP oracles suffice for the general functional synthesis problem? I don't know. Another one is, which is sort of more the motivation for this talk, can I identify some interesting family of these Skolem synthesis problems for which you can solve without any oracles, so just like straight up in polynomial time, right? Sort of as low as I was able to go here was using an NP oracle, but can I come up with some other maybe natural but limited family of these problems that I can actually solve? I don't know. All right. With that, I conclude. Thanks, everyone. I look forward to hearing about your problems.
You're using an NP oracle. Does the oracle go in the circuit, or do you have to, can you only use it to find the circuit?
I was only using it to find the circuit.
Okay.
For some other kind of protocols, I think, like range avoidance or something along those lines. Or something completely, maybe I'll have to apply after thinking about it more than 10 seconds.
Okay.
The trend avoidance doesn't seem to come in each other.
The third one is not for unique Skolem synthesis or unit function, but the whole form.
This was not unique. Yeah, but there's a very small number of existentially quantified variables.
Right, but they're inside.
But
I guess you said you didn't know bound, but particularly the obvious question would be something like this approval in T22 or A through C2, like you say, it's working way down, but be interesting. You're verging on proving some sort of collapse of the law of my hierarchy and push this too much further, so it'd be interesting though. Might use that as an up and down the way you should expect to prove.
yeah, I mean, I'm not, this is not, work aimed at collapsing the Palmer time hierarchy.
I wouldn't ask bypass the result if you find it. but-
No, I mean, I wouldn't, yeah. I would still try to publish it.
Yes, bouncing off of Sam's question, and Mark, can you phrase this sort of in terms of simulating TF sigma 2 in terms of TFNP with oracle access?
Tentatively, I'd like to say yes, right, because if you gave me the, so something with TF sigma 2, I could try to reduce that to the, right, obviously to the sigma 2. Oh, wait a minute, you mean pi 2 or sigma 2? These are pi 2 formulas, right, because it was a,
Well, you have pi 3 formulas here, you've got relatives for all.
oh, you mean in the, no, well, in the final part, you can have like for all is for all, but then the number of bits under the exist is very small.
So I guess like under which. So obviously you can't do this in general, because otherwise you're gonna collapse things that shouldn't be collapsible.
Right.
But I guess which of these problems, you've given instances here where you can do Skolem synthesis.
Mhm.
So which problems can you phrase in this manner, like collapsing, well, not collapse, but simulating TFM problem.
Right, I mean, so again, oh, I see. Actually, so right, so the difficulty here was that the thing that gave me the general, like, pi 2 simulation was using the unique functional synthesis oracle where I didn't necessarily get a polynomial size representation out. Right, I just said, oh, you know, I'll be polynomial time in the output of the oracle, whatever that is. Okay. And we were only able to do like the K anchored relations using the NP oracle. Right. So, like, sure, if you, I guess, yeah, fine. If you could get this with general functional synthesis with the NP oracle, yeah, I guess that would look like a collapse, wouldn't it? Of a pi 2 to like, yeah, just P to the NP. So shouldn't expect that to happen.
Maybe I'm not understanding, but, so like say that you start with a problem like in UP,
Mhm.
prime factorization.
Right.
So and you define like the formula that says something like Y is a prime factorization of X,
Mhm.
and you know, have some convention, so there's a unique prime factorization.
Right.
And you prove that. Okay, but still, if you could find a Skolemization, right, wouldn't that give you a circuit that solves, right, you know, solves
They can
factoring?
make a lower bound for the kind of things that are really solution.
Okay. So is it, okay, so,
The with the formulation of the lower bound.
No, but that is interesting yeah, I mean, you know, for this intermediate or result in the middle for unique synthesis, that, yeah, you can enforce that the factorization is unique. And then that would say that, NP can find for me
a
polynomial-sized circuit.
that factors.
Well, okay, no. Good. So here's where you,
Okay,
if there is no such circuit, right, so that's only when there is such a circuit to find,
okay,
right? Eventually, I might just like kill all the circuits and then say, oh, sorry, you know, try again, right?
okay.
'Cause
so
eventually
you want-
sampling might just fail.
So, okay, so maybe I misunderstood. So the problem is to find such a circuit in the that's polynomially related to the minimum size such circuit, not necessarily polynomial time overall, polynomial size overall.
Well, ultimately, you would like it to be polynomial size, so sure, you know, this is gonna be polynomial the size of the circuit. If I do this iterative, increase in the size. Right. Yeah, because, right, so what happens is at the end, you check if you got something that was a correct Skolem function or if there is a counterexample, right? In the case where, like, for factoring, oh, there was no small circuit that factored for me in the first place.
Right.
You end up with garbage here, you might say, okay, fine, let me increase my size bound.
Yeah.
And then I might run, I mean, this is not necessarily gonna be minimum size, right? Because I've still sampled like a linear number of circuits and taken a majority here, so it's slightly worse than minimum,
Okay, but
okay?
you want it to be related to the.
But yeah, up to like, say, a linear factor, it might be minimum size. So it's approximate minimum circuit size. I guess it ended up being related to the MCSB after all. Sorry.
I do not work on meta complexity. I work on things that are adjacent to it. I knew that there was gonna be 5 minutes, so I'm giving a talk the day after tomorrow. So there's gonna be a whole bunch of other open problems in that, which are perhaps more sort of interesting.